start with the introductions, basic introduction I talk about here. So a little bit in more details. So basically, we still deal with the same single degrees mass spring damper system, and under the force. So we're still looking for the steady state response. That is our focus. And rather than harmonic, FT can be a general. You can think about what general, that would be any general. Okay. This is our contents. In chapter 3, we've been dealing with this one. And in chapter 4, in the current chapters, we're going to introduce 2 new tools in convolutional integral and the Laplace transform. Basically, the both are the same. Okay, this will be in second part, in the part 2. Okay, this one will be, we won't touch it until maybe 3 or 4 lectures hours later. Okay, so that is the big pictures here. So this is the part 1. So we're going to study how to determine the steady state response of XP, okay? And respect to F, the force is in this form. So this form, if you look at this carefully, and this is, for example, this is a constant, okay? And to solve a steady state response to a constant loading, that is easy. I will show you. And this portion is a combination of the harmonic functions of different omega. Okay, for example, cosine omega t, cosine omega 2, j equal to 1 to infinity, cosine omega t, cosine 2 omega t, cosine 3 omega t, etc., etc. Okay, so that means we have multiple frequencies. And how to solve for this kind of problems for steady state response? And here I'm going to deliver the key information. And if you like, you can, using the big font, write into your lecture notes. Because the system is linear, we can use linear combinations method to combine the response to different frequencies together. Be good? So linear combinations of the different response. That's it. In details is this. So this is a concept, and let me show you these things here. So our systems, we have okay. So in chapter 3, we have learned is this. For example, this is F now, and then say E. I omega t. Okay. So in chapter 3, we have learned is this. So we're using the transfer function method to demonstrate the concept of the linear combination or linear superpositions. So the transfer function of the system is this. So this is our input, and this is our output. The transfer function right now let me to directly jump into the expressions, and that one basically is equal to, let me write it up here. The transfer function basically is equal to ms squared plus cs plus k, right? So that is our output with respect to input. That is the transfer function of the systems. Then we simply replace this equal to j omega, so that's equal to k minus m omega squared plus j c omega, right? So this one, if we express in terms of the magnitude and the phase angle, Then here, let me express in terms of the magnitude and with phase angle. So the magnitude will be equal to, let me write it up here. K minus m omega squared plus c omega squared, right? Okay, and then the phase angle for this one equal to arctangent. Here we have a minus, okay, and I explained that in detail. Look for that handout. So that information, and right now we simply filled up the what is the input. For chapter 3, we have learned this is F0 E I omega t, so the phase angle is omega t. That is our input. And so that means the output is obtained by, output has a magnitude that's equal to the magnitude of the input multiplied with the magnitude of the system. Okay, so let me not just write up here, I just replace the whole thing here. The phase angle of the output equal to the phase angle of the input plus the phase angle of the system. Okay? Good. So that is from our chapter 3. Chapter 4. So we have multiple frequencies. For chapter 4, we have F1, E, I, and say here I have a notation of omega 2. So omega representing is the different frequencies plus F is F1 and say F2 E I omega 2T plus etc. So omega 1, omega 2 simply indicate the different numbers than this one. For example, this is omega. You can imagine this is 2 omega, 3 omega, etc., etc. Okay. So here we have a combinations of different loading because this is a linear system. The linear system is such that the system substitute the response to individual, we have this one. So here is the superpositions. So we substitute the loading, the second loading is F1, the frequency is F1, okay? So the output will be corresponding the system's response to this one will be equal to, again, the magnitude of the input multiplied with the magnitude of the system. The phase angle is a summation of this plus this. And again, let me skip off the phi. Okay, so here I replace phi by this. If we have another input like this, omega 2t, then here we have a system F1 and F2 m omega, and again the form will be like this. Okay, and this is a superposition of the combination of the input is like this plus, and we have plus this one. This is a linear system, so the response to individual input will be equal to the output, will be the summation of that individual output. Okay? So that is a concept. So the whole thing in this page actually displays the key concept. Because the system is linear, we can use the superposition principle to first decompose the system response to individual components of the force. Then once you have an individual output, then you simply take the summation together. That's it. So in this way, you can imagine basically is we multiply our calculation rigorous multiple times, and in each part of the calculation simply is a repeated work you have learned in chapter 3. Does that make sense? Okay, so so I think in this way I finished the first portion of this part. Then maybe next coming back we can look for some examples here.